can everyone see that?
Yep. Yes.
Okay, so as discussed, I'm from NIAR Atlas, giving a talk on some of our rapid manufacturing research that we're doing. Little mission statement of NIAR, strengthening the university research capabilities, and we're really heavily focused on interfacing with industry and helping with research and all of their manufacturing needs and material research needs, helping drive up TRLs of new manufacturing processes. Quick overview on the Atlas Lab within NIAR. The Atlas Lab was started in 2019 with getting our new equipment in 2020. So all of these capabilities have been built up since 2020. We started out with more traditional automated fiber replacement equipment with a Coriolis C1 8-toe 1/4-inch head with a creel house, like a standard Coriolis unit. And then we transitioned into some electro-impact AFB equipment with interchangeable heads, so we can utilize more material formats, 1/4-inch toe, 1/2-inch toe, as well as single lane ATL wide format materials, 6, 9, 12-inch wide, as well as multiple material types with our different heat systems, infrared lamps, hum3, visible light pulse lamps, and laser heating for thermoplastics and dry fibers. In-house slitting capabilities for rapid turnaround on material research. We can go directly from wide format spools made by material manufacturers to running on our AFP equipment. And then some of the technologies that we're actually going to be talking about today with the rapid manufacturing is thermoplastic stamp forming and overmolding, as well as this MicroSam dual robot toolless technology, which is a very unique system, and electro-impact scram type equipment, where it's basically a factory all in one machine for rapid turnaround of tooling. So some of the main technologies I'm going to be giving an overview of today is toolless in situ consolidated thermoplastic, which is with the MicroSam dual robot system. That allows us to create contoured components without having to design and build layup tooling like you do with traditional AFP. The scram machine I was talking about before allows you to have rapid turnaround, low-cost tooling, as well as break apart or melt out tooling for complex components where your tooling ends up trapped inside of the finished component until you can disassemble it in smaller pieces to pull it out. And I'm also going to be covering some of our thermoplastic stamp forming and overmolding capabilities, which really lends itself to high rate part manufacture. And that's common in automotive industry, but we're working on transitioning that to the higher temperature engineering grade thermoplastics for aerospace use. And then I'm also going to give a brief overview of standard autoclave cycle process optimization with microwires. So the first technique we're going over here is the MicroSam dual robot system. So you'll see in the center picture we have two different robots. The one on the right has a single lane ATL head, which is capable of laying thermoplastic material with a laser heater, which is at the bottom of the head here. This is set up to lay a 1-inch wide strip of unidirectional thermoplastic material. And the second robot over on the left is actually just a support robot. This is kind of similar to like an English wheel and sheet metal forming, where you are forming from one side and supporting from the other. But what this allows us to do is starting and ending from a fixed reference frame, which is what these two aluminum panels are, top and bottom. The two robots come together at this top panel, and then they drive through space with the ATL head melting the material as it comes out of the ATL head, and then it's cooling and recrystallizing on the support roller in space, so we can create these contoured parts without having to create a tool. We're pretty much only limited by the reach of the robot and inside of this layup frame we have right here. And if we go to the next slide, I have a video where you can see the process in action. So this is the first course of a toolless panel. You can see the two robots are working in concert, and they're going from one end of this reference frame to the other to minimize the material wasted for the given contour. We designed these profiled support starting and ending reference points, which are basically just projections of the edge profile of the part we're creating. And those are real cheap laser cut sheet metal tooling. It's just bolted together, and from the structure of the sheet metal that forms the contour of the panel we're making. This particular panel that we're manufacturing in this video is a concave 100-inch radius swept along a convex 50-inch radius. So that's kind of similar to what you might see on like a wing skin type curvature. On this first ply here, to get the structural rigidity of the first ply, we actually overlap course to course for that first ply by 2/3 of the course width. That prevents the toes from wandering out side to side as we're doing this layup. It does mean that we, for this particular part, we end up with 3 0 plies when we start the panel. So that is the only one of these machines in the world currently that can do this toolless manufacturing. So here's an example single curvature part that we manufactured on this machine. Extending above and below the edges I'm highlighting here is just that essentially 3-layer thick base ply, and then we've built up to a 12-ply thick panel in the center here. And then we have some like a T-scan data to basically show the accuracy of the curvature of this part. This is still a very much in research technology here, but there's some promising results as far as part accuracy. This gray line is fitted to the curvature of the part here, and it came out to a 51.78 inch radius compared to a 50-inch nominal. So you're seeing kind of a similar level of spring back that you see when laying up on a tool, as far as like a couple of degrees of spring back. And then when fitted to a perfect cylinder, this color chart shows the deformation in and out of plane, ranging about plus or minus 70 thou with the current process. So that was a single curvature part. And then from there, we moved on to the double curvature panel that I was describing before, which is the convex curve swept along the concave curve. And our kind of next near-term goal with this manufacturing technology is actually to use it to create well, it's a wing skin is what's modeled here. But before we actually, try and create a wing skin type part, what we're going to manufacture is the face sheet of a tool for curing a thermoset wing skin part. This will allow us to, rapidly manufacture a composite tooling face sheet with without having to build a mold to create that face sheet on. and then any small deviations in the profile geometry of that part, we can deflect out of the part by attaching it to a fixed egg crate backing structure. So that was the toolless in-situ layout. And the next technology I'm going to be talking about is using the electro-impact scram machine, which basically combines a large number of 3D printing technologies as well as subtractive machining and automated fiber placement. So the particular capabilities of this machine is there's a single lane AFP head that can do 1/4 half-inch wide thermoplastic and then on that same head you actually have dual filament extruder 3D printing heads. So you can do a part like what's pictured here at the bottom, where you AFP a skin and then you AFP a thermoplastic skin, and then you extrude on top of that a variable density core structure using the filament extruder, and then you can come back and encapsulate that with another thermoplastic AFP skin, so you can fully print a complete, rigid core structure. In addition to that scram head, it also has a large format printing head, which is a pellet extruder for doing large acreage prints like the inside of this serpentine duct here, and then a milling spindle, so we can on the same machine print it out and then profile mill the surface of the tool to ready it for layup. So this is pictured here is one of the first 3D printed tools that we've printed on this part. This is right after print, prior to machining. This particular tool is a ABS print with glass fiber reinforcement. So after this gets machined and a little bit of surface prep as far as just like hand sanding to get the surface finish you want, we'll be able to do a low temperature thermoset material cure on there, and then we can actually submerge that entire ABS print in an acetone bath and melt the tooling out of the part. Some of the other options we have include PVA, where we can do a water soluble tool so we can avoid the acetone mess. Pictured here are some of the different paths you can run using this technology. So we do the polymer printing of the tool, profile mill it with the same machine, do a little bit of surface prep, and then we can go one of two directions. You can either do an in-situ layup with a thermoplastic, which will stick to the ABS tool pretty well, get as good of in-situ consolidation parameters as you can on there, and then melt the tool out, and you end up with a finished part straight off of one machine. Or we can also use a higher temperature 3D printing resin, where we can do an autoclave or an oven cure of a thermoset material, and then either build it in segments or break out the tool from the finished part. Or in the instance of this spar here, it's non-locking geometry. So this is a 3D printed spar tool design, which is printed onto a back of a rigid steel mandrel. So you put the mandrel on a horizontal rotator, print the body of the tool with the pellet printing head, profile mill it, and then the tool is something like a carbon fiber reinforced PEI resin, which we can do a 350 cure thermoset on. The example tool designed on the right here is the same geometry as the rear portion of this serpentine duct that's on the left, but done in such a way as to put it on a rigid steel core, and that is to interface with a standard AFP machine horizontal rotator for doing higher rate AFP manufacturing compared to the single lane AFP manufacturing that we can do with the scram machine. In this instance, this would also be a melt out tool. with this 4-segment serpentine duct. The third region of rapid manufacturing research we're doing is with thermoplastic stamp forming and injection molding. Pictured here is a Engel 1900-ton injection molding press. Platen size, as you see here, is almost 6 feet wide by 7 feet long, and there's 6 feet of daylight in between those platens. And we've been retrofitting this machine to run with the higher temperature, PEEK-based thermoplastic materials for doing stamp forming and consolidation of panels. And then the same machine, in addition to the stamp forming capabilities, it also has high temperature injection molding, which is this unit off to the left of the machine, which is a screw extruder and then a hydraulic ram for injecting through a hot runner system, so that you can reach all the different parts of your mold component. And then, in addition to that, on the backside of the machine, there's also a high pressure resin transfer molding pump, where we can take a dry fiber blank in an encapsulated mold and inject it with a thermoset resin. This example part on the right here is a thermoplastic cloth blank that's been stamp formed in this shape, and then it gets transferred to a second mold where this green material is injection molded on top of it. That's a chop fiber material for your stiffening ribs and mounting features. Like I say, there's a lot of research is being done with the types of materials this can be done with. This technology is widespread in automotive, and they churn out multiple parts, or a part every couple of seconds. But we're retrofitting this technology to higher quality, higher temperature materials required by aerospace. And this is a second stamp forming injection molding machine, which has a lot of the same technology with a couple of additions. This machine allows us to have 2 different molds where the central mold spins 180 degrees to expose it to 2 different cavities. So you can actually do multiple layers of injection molding. Or you can get a chop fiber structural reinforcement in one mold, or flip it around and expose it to the color form injection system, where you can get a Class A finish in whatever color and surface texture you need, so you can get basically finished parts directly off the machine. Some of the advantages of doing this press consolidation versus autoclave and oven for thermoplastics: cycle time is the big one. Autoclave consolidating your high temperature thermoplastic materials, you only have to maintain the 720 degree temperature for 20 or 30 minutes to get your consolidation properties. But you have to remember there's the entire ramp up and then ramp down of the temperature, so your actual cycle time ends up being quite long despite having the real short dwell. This is one of our example thermoplastic cure cycles. As you can see, that's more than 500 minutes long. And with these PEEK thermoplastics, we're not getting automotive cycle times in our press, where it's every couple of seconds they're making a new part. But also in aerospace, you don't need that kind of manufacturing rate, so we're able to slow it down if we need to, and spend a little bit longer at temperature, build up the crystallinity and the material properties that we need, and still get a massive return on part rate versus autoclave type process. There's also drawbacks with the vacuum bagging materials you need to be able to survive 750-degree air temps in the autoclave, and that your bagging materials are extremely expensive, and they're also less forgiving than your traditional thermoset bagging materials. So you end up with a higher failure rate of your vacuum bags, as well as the materials themselves costing 10 or 15 times more to create that same vacuum bag. And they're also less forgiving of complex geometry, because the polyamide bags don't really stretch. And then there's also energy savings on a per part basis with, how much less time you have to spend heating that volume. And the last rapid manufacturing process I'm going to cover here is more of your traditional thermoset process. This is called a microwire system, where you embed this small temperature reading device inside of a trial run. This is a sacrificial thermoset part that you would be doing this on, because you will have this part embedded in it. But you embed these sensors anywhere that you are going to have where it's going to take the longest for your part to heat up. And when you embed these sensors inside of the part, let's say there's more tool mass behind a certain region, or if that's the thickest part of the buildup, then we have these wireless sensors embedded in the part that's going through the autoclave cycle, and that temperature is fed directly into an external rheometer, where we have a stack of the exact same layup sequence, exact same batch of material, and then we can measure the degree of cure and the viscosity of the material by driving that sample to exactly the same temperature as what's inside the part. And what that allows you to do is fully optimize your autoclave cycle. So your recommended cure cycle is going to be kind of conservative, based on, they don't necessarily know how thick your final laminate is going to be. They don't know what kind of tool geometry it's going to be on. And this will let you, reduce your dwell times and increase your heating rates to the shortest extent possible, so you can fully optimize your traditional thermoset cure cycle. So just in conclusion, the technologies covered today was the toolless in situ consolidation of AFP, rapid tool manufacturing using 3D printed tooling with an electron pack scran machine, as well as thermoplastic stamp forming and overmolding, and optimizing autoclave cycles using embedded microwire sensors. So, any questions?